Hello, dear students. I welcome you all for the online lecture series of Design of Steel Structure. In today's lecture, we will be learning regarding the laterally supported and unsupported beams. First of all, let us learn what does mean by a beam. A beam is nothing but a structural member subjected to the transverse loading, that is, the load applied perpendicular to the longitudinal axis of a member. These members are placed horizontally and subjected to the vertical loading. The load transmission mechanism is due to the bending and shear, hence the element is called as beam element. If you observe the diagram which I am highlighting is a diagram of a beam which is loaded transversely. Then there are different examples of the beam section. First one is joist, then a girder, a purlin, a lintel and a stringer. Let us see one by one these elements. First element is the joist. When used in a building to support a roof, it's called as an joist. This is a diagram of a joist. See here, these are the joist. Then member supporting number of joists are termed as a girder. See here, these number of joists are supported by a beam, and that beam section is called as an girder. Then the member carrying roof load and roof covering load are called as an purlin. Here is the diagram of purlin. Over this purlin, the roof covering are being mounted. Then the member carrying load above the opening are called as lintel. Dear students, whatever the structure which is constructed above a above a window, above a door, that structure is called as an lintel, and it is also a small beam. Then the stringers are members in a bridge aligned in the direction of a traffic. Then our area of interest, that is laterally supported beam and laterally unsupported beam. In previous slide we have learned what does mean by beam, and now we are going to learn what does mean by laterally supported beam and laterally unsupported beam. The lateral buckling of the compression flange of a beam is restrained in the case of laterally supported beam. Here, my dear students, the top compression flange is directly being embedded into the slab, or studs are mounted on this top compression flange and that studs are being embedded in the slab, or the bracing is done in such a way that the top compression flange remains restrained against the buckling. The floor slab beams bracing system provides the lateral buckling which restrains the buckling of the section. Then the buckling may be laterally for the total cross section in the case of flange or in the wave portion. The laterally unsupported beam. The lateral buckling in the compression is the possible. Compression flange is possible. No such lateral restraint is available in the case of girders, and hence the buckling occurs laterally. If you observe this diagram, the top compression flange is not being supported or not being restrained. Hence this top flange may buckle, and hence the section is called as laterally unsupported beam. Then we will be studying the design of laterally supported beam. It is designed according to IS 800-2007. First of all, for designing any structure, we need to calculate the effective span of the beam, and it is calculated from clause number 8.8.1. The distance between the center of the supports or the length between the assumed line of reaction. If B is the width of the support and L is the clear span of the beam, then L effective is equals to L plus B by 2 plus B by 2, that is L plus B. The bending and the axial force acting on the section may be assumed to be resisted by the flanges only, and the web is designed to resist the shear only. Dear students, for designing a beam, I section is considered as an ideal section. The reason of it is in the second statement, that is, the flanges resist the bending moment and the web resists the shear force. The shear strength of the section is calculated from clause number 8.4. Here, the factor design shear force V in a beam due to the external action shall be satisfying the condition V should be less than V design. That is, Vd is equals to design shear strength, and it is calculated by using the formula AV into Fyw upon root 3 gamma m0, where AV is equals to H into Tw. It is nothing but the area of the web, my dear students, and AV is equals to small d into Tw for the welded section. Here total depth is taken, and here in the case of rolled steel section, the inner to inner depth is taken. Then for the factor design shear force does not exceed 0.6 Vd, the design bending strength Md can be calculated by the formula from the clause number 8.2.1.2, and this Md is equals to beta B into Zp into Fy upon gamma m0. To avoid the reversible deformation under serviceability load, Md shall be less than 1.2 Zefy upon gamma m0 in case of simply supported, and 1.5 Zefy divided by gamma m0 in case of cantilever B, where beta B is equals to 1 for the plastic and compact section. We have to classify the section very previously. We have learned the classification of cross section. That from that we have to calculate whether the section is compact or plastic or semi-compact. From that we have to decide the value of beta B. Beta B is equals to Ze upon Zp in the case of semi-compact section, where Zp and Ze are the plastic and elastic section modulus of the cross section respectively. Fy is yield stress of the material, and gamma m0 is partial factor of safety, and we have to check clause number 5.4.1 for it. Then when the design shear force Vd exceeds 0.6 Vd, when the design shear force, factored shear force V exceeds 0.6 Vd, the design bending moment Md shall be taken as Mdv, means it is a case of a high shear, and Mdv is equals to Md minus beta into bracket Md minus Mfd into bracket, and it should be less than 1.2 Zd into Fy upon gamma m0. Beta is equals to into bracket 2V minus upon Vd minus 1 bracket square. Md is plastic design moment of the whole section disregarding the high shear force effect, and it is calculated by clause number 8.2.1.2, means this formula. V is the factored applied shear force as governed by the web yielding or the web buckling. Vd is nothing but the design shear strength as governed by the web yielding or web buckling, calculated by clause number 8.4.1 here. Then the design shears, the MFD, that is the plastic design strength of the area of the cross section excluding the shear area considering the partial factor of safety gamma m0, and Z is the elastic section modulus of the whole section. For the semi-compact section, mdv is equals to Ze Fy upon gamma m0. Then the next step is the resistance to the shear buckling. Clause number 8.2.1.1. When the flanges are plastic, compact or semi-compact, but the web is susceptible to the shear buckling before the yielding, that is, the ratio of d upon tw is less than or equals to 67 epsilon. In that case, there is shear buckling. The above ratio is not satisfied, the shear buckling will be occurring. Now we will learn how to check the beam for shear web buckling and web crippling. Whenever the beam in a rolled section behave like a column when placed under the concentric load or the reaction, as the web is thin, therefore it is subjected to the buckling. If you observe this diagram, there you will observing these are the patterns of the web buckling. The web buckle like a column here. 1, 2, 3 and 4. This is 1, this is 2, this is 4. Now the web buckling is calculated by the formula FWB is equals to B into TW into FCD. For FCD, lambda is equals to 2.45 under root of, into bracket D1 plus TW, and from table number 9C we are calculating the FCD. TW is the thickness of the web and B is the bearing length plus D by W for the reactions, whereas B is the stiffness bearing length plus D in the case of concentrated loading. Here you will be observing a concentrated loading. This is the B, that is the stiff bearing length. D small d1 is the distance, that is the height of the web, and capital D is nothing but the total depth of the section. Next, check for the web crippling. The loads and the reactions concentrated along the length of the flange of the beam are registered by the compressive stresses in the beam. The stresses concentration occurs at the junctions of the web and the flange. The web near the stress point tend to fold the flanges. If you observe in the diagram, here the concentrated load is acting on the section and there will be a crippling at the points. These are the two cases of the crippling. So the bearing against the crippling is calculated by the formula FW is equals to A into FYW upon gamma m0, where A is equals to effective area of the web, which is equals to B1 into TW. B1 is equals to B plus twice N1 for concentrated loading. B1 is equals to B plus N1 for the reaction at the support. N1 is equals to 2.5 TF plus R1. TF means thickness of the flange, R1 root radius 1. Then the third and the last check for designing the beam is the check for the deflection. If you observe the figure, you will be getting how to give the check for the deflection. In the case of simply supported beam, this is the formula, and in the case of UDL, this is the formula for the Deflection. A small deflection of the beam does not cause the structural problem in general, but the excessive deflection may lead to the crack and damage to the attached material. For simple span upon 300 to span upon 240, and for the gantry girder, span upon 500 is a permissible limit for the deflection. Dear students, this is the method to design laterally supported beam for a high shear and for a low shear. We will be solving detailed numerical on based upon this theory in the next lectures. Till then, keep watching, subscribe the channel. Thank you.